Welcome to episode 1 of the proof series. Here we will prove different identities from this unit. Today we will be proving the addition identity of cosine, which states cosine of x plus y is equal to cosine of x times cosine of y minus sinus x times sine of y. To illustrate this proof, I will be setting up a unit circle to help us. I plotted 4 points on that unit circle. The following points are p sub 0, p sub 1, q sub 0, and q sub 1. I have plotted them in specific places to help us get to where we want to go and make it easier for us to prove. Now I've located them in specific spots, so I will kind of explain how I got there. So the points are p sub 0 is located at 1, 0. I gave us a nice point to kind of start with, one that I actually know all the values. The others I do not. They are stated at different angle measurements, and I'm going to be using my trig identities to help me. And remember that cosine represents x, sine represents y. So based on the angle measurement of where the points are located on the unit circle, that's what I'll be using to help me figure out what those values or ratios are at those. But I will never actually find them because we don't have any actual angles that we'll be using. But for our proof, we want to keep it as general as possible as well. So for q sub 0, cosine of negative y, comma sine of negative y will be my ordered pair. So negative y is the value of the angle that I'm at for that point. Now this one can be simplified a little bit because cosine is an even identity, which means that if you have a negative angle in for your cosine, it's the same thing as the positive angle. So I can actually write that as cosine of y. Sine is an odd identity, so which means that when it's a negative angle, I can rewrite it as the negative sine of a positive angle. For p or the point p sub 1, it's located at the angle of x plus y. And so there's no simplification there, but I can represent it as cosine of x plus y, comma sine of x plus y. And then for the point q sub 1, it's located at the angle measurement of x. So I will be saying that it's cosine of x, comma sine of x. Now how did I get these? So I also denoted the distances for each of these arcs as variables to give us some wiggle room and also make it general because I don't actually know what these are. So I'm using variables to help me kind of generalize the distances. So I denoted the following arc measurements for points p sub 0 to q sub 1 to be x. For the distance between q sub 1 to p sub 1 will be y. For the distance between p sub 0 to q sub 0 will be negative y. And the distance from p sub 0 to p sub 1 will be x plus y. Now I know that it doesn't look like on the unit circle that certain arc lengths are going to be the same, but actually there are. So I've denoted that p sub 0 to p sub 1 is x plus y, but in fact q sub 0 to q sub 1 is actually the same. So if I use distance to kind of help me out, taking those values of x minus the value of negative y, the double negative changes it to positive, so it's actually x plus y as well. And because they are equal to one another, I'm going to use a geometry fact to help us set up our proof here today. It's said that equal arcs subtended by equal chords. So what this means is if you have two arcs that are equal in length, then the chords that can be created between those points are equal to each other. So remember that a chord is a line that connects two different points along the outside of the circle. So using this theorem, we can set up an equation that states that the distance between p sub 0 to p sub 1 is equal to the distance between q sub 0 to q sub 1. Using the distance formula, we can make this equation while using the points that we have already set up. And remember, we want to be able to find cosine of x plus y on the left side of this equation when we're done. So try to keep that in mind as we move through the simplification of this equation. So when I plug all that stuff in, the equation that I get is the square root of cosine of x plus y minus 1 in parentheses squared plus sine of x plus y minus 0 in parentheses squared. And that is equal to the square root of cosine of x minus cosine of y in parentheses squared plus sine of x minus negative sine of y in parentheses squared. Okay, now the first thing hopefully you notice is that we don't need the minus 0 on the left side, so we can kind of get rid of that when we simplify. Also on the right side, that double negative, because the parentheses of negative sine of y is not necessary, so double negative makes that positive, so that's one thing to keep in mind. But what we want to do to continue here is square both sides and multiply out our binomials to get us the following equation. So now I have cosine squared of x plus y minus 2 cosine of x plus y plus 1 plus sine squared of x plus y. That equals cosine squared minus 2 cosine x cosine y plus cosine squared y plus sine squared x plus 2 sine x sine y plus sine squared y. Using one of our Pythagorean identities of sine squared plus cosine squared, which equals 1, we can use this to help us simplify our equation further. So then we are able to take all the cosine squares of like angles and simplify them down to 1. So there is one set on the left of cosine squared x plus y and sine squared x plus y that make a 1. On the right there's two sets. So cosine squared x, sine squared x makes a 1, and cosine squared y and sine squared y makes a 1. So then I get the following equation of 1 minus 2 cosine x plus y plus 1 equals 1 minus 2 cosine of x cosine y plus 1 plus sine squared or sine x sine y. Then from here we want to subtract the values of 1 on the left to move them to the right, which gives us negative cosine of x plus y is equal to negative cosine x cosine y plus 2 sine x sine y. With one last step, we want to divide the negative 2 from the left to everything on the right to get our identity of cosine of x plus y in parentheses is equal to cosine x cosine y minus sine x sine y. That is the proof for the addition identity of cosine. This setup can be used to prove the other addition and subtraction identities for sine, cosine, and tangent as well, with a little tweaking. Thanks for watching.